Hello, everyone. Welcome to today's webinar. Before we get started, if you can hear me okay, please raise your hand in the GoToWebinar control panel to your right. Okay, see hands going up. Great. Thanks, everybody. We will be recording today's webinar, and we will send a link to the recording as well as a link to today's slides out to your email in basket within the next 24 hours, so please watch for that. If you have any questions during today's webinar, please put them in the questions panel in the GoToWebinar control panel, and we'll answer as many of those as we have time for at the end of the presentation. With that, I will turn it over to you, Dennis.
Yeah, hello everyone. Hi, Terry. As you can see, guys, today we are going to talk about in-memory computing, and specifically, we are going to focus on so-called essentials. What are the essentials? Those are some of the critical concepts that are related to various in-memory computing technologies. And the goal of this session is to equip you with all the knowledge you should have if you are going to start building your first solutions using in-memory caches, in-memory data grids, or in-memory databases. And before we start and look into the agenda, let's raise the question of why in-memory computing technologies are getting so much traction today. Why companies big and small deploy in-memory caches, databases, and platforms to accelerate just simple applications as well as mission-critical applications. And I would refer to some of the precise numbers using this handy table. As you can see on this table, it goes with 3 columns. In the first column, we are listing some of the system events, such as CPU cycles, level 1 cache access, SSD I/O, etc. In the second column, we can see actual latency time. How much does it take for a CPU to complete one of the operations to the left? And what's interesting, in the third column, we are trying to scale this actual latency to the units that can be perceived by us as humans more naturally. Because we as humans, we know that nanoseconds, microseconds, and milliseconds are extremely low units and measurements, but our brains, our mind cannot fully appreciate how vast the difference between nanoseconds and microseconds, for instance. And that's why once we take this formula, if to assume that one CPU cycle that usually on average takes 4 nanoseconds to complete is equal to 1 second in our scaled latency, then we can approximate the rest of the operations latency times. And once this happens, let's quickly look at a couple of rows. We can see that main memory access is tremendously faster than disk I/O operations. How faster? It's like the difference between minutes and days and months. That's how big the difference between nanoseconds and microseconds. And that's why in-memory computing technologies like caches, one of the primary reasons why in-memory computing technologies like caches, databases, and data grids are being deployed so broadly by various companies. And that's probably why many of you are attending this webinar today, because you heard that in-memory computing uses memory as a primary storage layer, and if you do this, you can get significant performance boost for your applications. And that's probably why. That's why, because the numbers, CPUs can get the data, serve the data from memory much faster. However, before kind of revealing and discussing details of our today's presentation, let me give you a precaution. Because many of us, many architects and developers, once they see those numbers, they get so inspired that sometimes they falsely assume that once they deploy their first in-memory cluster and preload data there, they will get an order of magnitude performance increase. In some of the use cases, it will work out, but in the majority of scenarios, you still need to keep in mind some of the essentials. You need to know the best practices. You need to know common pitfalls. And that's why our agenda for today, when we are going to talk about essentials, I'd like to focus on 3 main pillars of in-memory computing. And these 3 concepts, like data partitioning, affinity collocations, and collocated computations, they're quite generic. Throughout this conversation today, we are going to use Apache Ignite as a reference platform, but nothing prevents you from using, let's say, other products from the same category, because data partition is pretty generic stuff. Affinity collocation is an approach that helps your distributed in-memory systems to avoid or minimize data shuffling over the network. And collocated computations is a special data processing technique that lets your applications to run data-intensive or compute-intensive calculations on your server nodes without any data movement between your application layer and your storage layer. All right, so having said that, let's buckle up and move forward checking these essentials. And as I said, Apache Ignite will be our target platform for the today conversations. We are going to dive into the details of every critical concept, such as partitioning or affinity collocation, using Apache Ignite as an example. And also I'm going to show you some of the code samples so that you can remember how theory works in practice. Those of you who are new to Apache Ignite is one of the top 5 projects of the Apache Software Foundation. So you can find Apache Ignite as the top 2 most project judged by the dev list activity, and also it's ranked as the 3rd most active project in the user list activity. When they are talking about the user base of Apache Ignite, and here as we can mention GridGain as well, there are no any limitation or boundaries. We can see that Apache Ignite is used across many industries. It's used in financial sector for transactions processing, for payment settlement. It's used in telecom. It's used in logistics and transportation. It's used in e-commerce and retail, everywhere. A lot of the value is being given by this project. When we want to talk about features, specific capabilities of Ignite, let's quickly check this diagram. I find it relatively instrumental. You can see that Apache Ignite is an in-memory computing platform comprised of many building blocks. I usually define 2 primary components in Apache Ignite. The first one is it's distributed in-memory data storage with persistence layer. By definition, Apache Ignite is designed to store your records, your indexes in memory. And also it can persist all your data with indexes to disk. When it comes to disk, you have 2 options. You can deploy Apache Ignite on top of your relational database, for instance, or you can use Ignite native persistence. I'll quickly show you the difference between those 2 persistence options on the next slide. And on top of this storage component, Apache Ignite community provided well-integrated APIs that know how the data is distributed, how the data is stored, and once you load your data, you can use SQL, you can do ACID transactions, you can train your machine learning models, you can run compute tasks, key-value calculations, and do many more calculations and operations. Everything you can see in the middle is available in Apache Ignite. It belongs to Apache Software Foundation, available free of charge. And to the left and to the right, in blue blocks, you can see value add-ons provided by GridGain. So if you need any rolling upgrades, data center replication, point-in-time recovery, that's what's available for you with GridGain. And to briefly mention, what are the primary use cases of Apache Ignite? The first one is Ignite is used as an acceleration layer for your services, APIs, or databases. So here it's a classical caching or in-memory data grid use case. You deploy Ignite in the middle of your persistence layer, and your applications can switch to Ignite. They load data there. They serve this data from Ignite much faster. And if it's needed, Ignite can keep your underlying databases in sync automatically. For instance, sending all the changes of the updates to your relational database directly, not asking your application to do that. Another use case of Apache Ignite is a classical in-memory database usage scenario. And here is, instead of any external database, you immediately enable Ignite native persistence, and Ignite becomes your single system of record database that keeps all the records on disk and caches as much data as possible in memory, depending on how much RAM you have. With this scenario, nothing changes from the API standpoint. That's just one configuration change. And your applications can use all the same APIs. They can run SQL. If you do SQL query, if any data is not available in memory, Ignite will go and read this data from disk automatically for you. You're doing nothing. You're just running your queries. And this capability of having a subset of the data in memory enables another great feature, which is instantaneous or fast restarts. If you store, let's say, terabytes or petabytes of data in your Apache Ignite cluster, and the cluster went down by some reason, it can be your maintenance cycles. Once the cluster is restarted, you don't need to wait while all those terabytes or petabytes of data are loaded in memory. You can enable your applications. Applications will read all the data from disk in Ignite, and the memory will be warmed up in background. All right, enough about Apache Ignite. That was a quick introduction, and right now the time is for the essentials. And the first one will be partitioning, the first pillar. And why do we need partitioning? Partitioning or sharding algorithms help us to take and use all the memory resources and CPU cores of our distributed cluster. And the cluster is a collection of interconnected nodes or virtual machines or physical machines. Before we start, let's recall and remember how relational databases operate. Usually, relational databases keep all the records on a single machine. And the goal of partitioning is to take all our application records and distribute them across a cluster of interconnected nodes. And now let's quickly check how partitioning works internally. Let's assume that we have created some table. And once you create such a table, Ignite will automatically split this table into a fixed number of logical partitions. You will have partition number 1, 2, up to 1024 by default. Once this happens, once you create this table and connect with your first application, once that application puts the first record in the table, that record can go to partition number 2. The other record can go to partition number 1. And as long as your application will be inserting more records into this table, those records will be automatically distributed across partitions. They will be assigned to specific partitions. The next step and the next task of the partitioning algorithm is to distribute these partitions across your cluster nodes. Let's take this example. We have started a 2 nodes cluster. I have Ignite node number 1 and node number 2. And what happens next is that partitioning algorithm will take all your partitions and will start distributing them across all these 2 nodes. For instance, partition 0 can be assigned to node 1, partition 1 can be assigned to node 2, and the same procedure will be repeated for all the partitions that actually represent your just created table. And this assignment happens again automatically in background. And once this happens, your records will be evenly distributed together with these partitions. So your application records are stored inside of these partitions, and these partitions are automatically spread across your existing cluster nodes. And final step and final question that we need to be aware of is how this transformation from a record to a node happens. And here is, let's review this example. Again, we have the same 2 nodes cluster. We know that those partitions of the country table are already assigned among those 2 nodes. And now my application inserts this simple record. I'm inserting some country. And that country record has code, name, and continent fields, columns. So what happens next? Once your application pushes this record into Apache Ignite, Ignite takes the value of your primary key, which is the code column in this example. It will use a special hash function to map this primary key value to one of the partitions numbers. It can be partition 1, partition 10, or partition 500. We don't know. And after that, once the partition is determined, Ignite will check partition's distribution map and will locate a node number which keeps a primary copy of this partition right now. And it's worth mentioning that this transformation from key to partition to node happens within the boundaries of your application process. At least this is how it works in Apache Ignite. So there is no any extra network round trip involved here. So in Ignite, there is no any specific name node or master node, etc. Your applications like Java, thick clients, .NET thick clients, and with the latest Apache Ignite release, thin clients support this transformation within the application boundaries. And once we know what's the address of the cluster node that should keep the primary copy of this record, your application will open the connection to that node. In this case, we decided that that record should be located on node 2, and that record will be added to that cluster node. All right. Now let's quickly jump to the practical part. So actually, that's the partitioning, briefly in practice. Partitioning helps us to take all the memory resources available in our distributed cluster and distribute all the data using the partitioning algorithm. So what we are going to do next, we are going to run a demo that will help us to start our first Apache Ignite cluster on our local laptop, and then load some data there and double check and briefly check how partitions are distributed. So what I'm doing right now, I did my homework. So I've downloaded one of the latest versions of Apache Ignite and unpackaged in my downloads folder. Then I navigated to the bin folder, and right now I'm going to start the first Ignite server node on my local laptop. So you can develop your Ignite-powered applications using your personal machine. You don't need to provision any resources, at least if you'd like to experiment with Ignite. So we can see that our first cluster node is up and running. That's my server node. Also, throughout this presentation, I'm going to use a web console tool. That's the tool that helps us to manage and monitor the cluster. I also decided to download this web console from GridGain website, and right now I'm starting these several utility processes that will connect my local cluster to the backend of the console. So let me open this console on the machine. All right, still connecting. Let's wait for a second. Yep, I forgot to start it before this presentation. But anyway, so everything went smoothly. That's a real-time demo, right? And things can delay for a little bit. But anyway, so not a significant delay. So now, right now, we can see that this console was able to connect to my cluster. That's my only cluster node. That's one node cluster. And the next step, I want to develop the simplest Java application possible. I want to connect to this cluster node and load some data using key value operations. So what happens here? That's my put-get example. I'm starting main function. Here is I'm using Ignite library, Java library, saying that the next node that will be started within this process will be a client node. So this application will not be storing any data. That's the configuration file I use. Let me quickly show you what's inside of this configuration file. Nothing significant, just some settings related to memory capacity and to their network configuration. So I'm just saying how much memory I'm ready to allocate on my local laptop. And also I'm saying that all the cluster nodes, servers, and clients will be deployed on my local network interface, and they will be sitting and listening on one of these port numbers. After that, Ignite internally will figure out how to connect all the nodes together. Next, let me start this application. Once this client node connects to the cluster, we are going to create cache. And in Apache Ignite, we use both cache and table as terms, and there are SQL APIs, the key value APIs, but in fact, cache and table are all the same things. You basically can use this and that, depending on your usage scenario. Once the cache is created, I'm going to use cache put, cache key value APIs to preload 40 records in my cluster. And once the data is preloaded, I'm just going to read this data back. What could be simpler, right? That's what can we do. Just connect to your cluster and load some data. So let me check, yes, the application could successfully connect to the cluster, created the cache, loaded data, read it back, and then shut down itself. Jumping back to the this monitoring tool, we can see that the cache, where is the cache? The cache, yeah, the cache is created. We have 40 records on the primary copy. I'm not setting up any backup copies for this during this webinar. And what I want to show you next is partitions distributions. Let me click on the partitions screen. And right now, as long as we have only one cluster node, it's not surprising that all these partitions, all 1024 partitions, are located on one cluster node, and all the records are spread across those partitions. The next exercise for us is to scale out our cluster. Let's assume that we want to scale it out. We want to allocate more memory. We want to give more CPUs for our applications. What do? I'm just starting one more Ignite node process. I'm using the same command. And again, I keep using my local laptop. So we are not demonstrating any performance benefits today. We are just showing you how you can easily start with developing your in-memory computing applications using your local resources. So the second cluster node was able to auto-discover the first one. So right now I have 2 nodes cluster. And if I refresh this partitions distribution screen, you can see that Ignite automatically completes several operations. First, once the second node connected to the cluster, Ignite partitioning algorithm automatically redistributed a subset of the partitions to the second node. So that's the current distribution. And after that, Ignite kicked off so-called rebalancing process. Rebalancing takes your records that are assigned and belong to one partitions and move these records together with the whole partition to the new owner. So generally what happened, 24 records were rebalanced from node 1 to node 2 because node 2 became the owner of 492 partitions. All right, so that's partitioning in practice. And generally, you don't need to do anything about it. As an application developer or architect, you just start your Ignite cluster or ask your IT team to provision the one for you. You can ask for some memory requirements, CPU course numbers, and then you just create your tables, caches, load your data. If you scale out your cluster, everything will be rebalanced, repartitioned for you automatically. So basically, that's how in-memory computing platforms and products distribute and use all the capacity of your machines transparently. Having said that, let's jump and proceed with our second critical concept of in-memory systems, which is affinity collocation. And why do we need affinity collocation? You've seen that in memory systems, like vast majority of memory systems, are designed as distributed software by definition. So with the partitioning, the goal of partitioning was to distribute everything across a cluster of machines. And what happens is that when you run key value operations, your application goes and reads data from one specific node, and that's like natural. That's how you can scale out, and that's how you can get your performance boost. But also, your application might want to run more advanced calculations. You might want to run SQL with joins. You might want to group data. You might want to scan data, and such complex or advanced operations can trigger data movement between your cluster server nodes, and you will start utilizing network more aggressively, because all the cluster nodes are interconnected through Ethernet or Wi-Fi, etc. And what's the problem here? Let's jump quickly back to the same table we used before. The table showed us that in-memory is much faster than disk, and that's why in-memory computing is getting traction, but also disk is much faster than network. Thus, if it happens that your application triggers a lot of data shuffling or data transfer, between the cluster nodes, you can literally diminish all the benefits of your distributed in-memory system. So what can we do about that? First, partitioning. By default, partitioning algorithm distributes all the records randomly. What it means? Imagine that we have created two tables right now. We have a country table that stores the records of all the countries in the world, and we have cities table for the cities records. And it can happen that all the countries, all the cities, sorry, that are located in the same country are not stored on the same cluster node. For instance, with this example, Toronto and Calgary as Canadian cities are stored together with the Canada record on node 1, but at the same time, Montreal and Ottawa are stored on node 2, just because that's how, because those records were mapped to the other partition. And here as we have the warning sign, because this situation might be okay for you, especially if you use just key value APIs when you need to read some individual records back. But things can go wrong, let's say, if you start using SQL with joins. And here is, you can imagine a variety of different in-memory databases that use providing SQL capabilities. So for instance, here is what happens. Our application executes a relatively simple SQL query that needs to join data stored in country and cities table. And during the join phase, what we have step 3. And with that step 3, there is data shuffling, there is data movement between Ignite node 1 and node 2, because node 1 doesn't have all the records, and the same is true for node 2. And this can cause performance degradation for your cluster, especially if you join relatively large data sets. And the goal of data partitioning is to help us as application developers and architects accumulate and store all the records that have some common relation on the same cluster machine. With this example of cities and countries, it's clear that there is a clear relation between these two data models. All the cities belong to one country. And with the help of affinity collocation, we'd like to ensure that all the Canadian cities are located on the same machine, and the same should be true for the cities of India. So how do we achieve such a collocated distribution? As application developers, it's really straightforward. Let's take this example. To the left, you can see that I'm creating country table using familiar SQL syntax. And with the second, to the right, I'm creating city table. Pay attention to the primary key. Yes, city has a compound primary key, which is ID and country code. And then we have some custom affinity key command. We are saying that affinity key, our affinity key for the city table, will be country code. So what's the influence of such a syntax? What happens next when you will be inserting, when your application will be inserting any city records into the cluster? Then instead of the ID, Ignite will be taking the value of your affinity key to map this record to one of the partitions, and then to map this partition to one of the nodes. Remember, right, this exercise. And it's quite understandable that all the cities that are located in the same country will share the same country code. And it doesn't matter whether you are inserting Ottawa, Montreal, or Calgary in your cluster, they have the same value for the country code. And that's why they will be located and stored together on the same cluster machine. So again, you as application developer, you just need to specify the value of affinity key. In this example, we use SQL syntax, but also Ignite provides APIs for Java level, .NET level, or XML configuration, many options. And that's it. After that, Ignite will take care of all the internals transparently. And once the data is collocated, that's what you are getting in return. We can run the same queries, advanced SQL queries with joins, and there is no more data movement between our server nodes when the join phase is executed. And with that simple optimizations, you truly can exploit all the capacity of your distributed in-memory cluster, not only for simple key value operations, but you can also run advanced analytical or real-time SQL queries, especially if there is no any data shuffling. Now let's check another example, right, to see how Affinity allocation works in practice. With the next example, I'm going to connect to Apache Ignite cluster. I already have these two nodes running on my local machine, and I'm going to connect to the cluster using Ignite JDBC driver and using SQL line tool. This SQL line tool is also delivered together with Apache Ignite distribution, and the same is true for the driver. So let me connect to the cluster. All right, the connection went well. And next, I have some of the scripts predefined here. Let me execute this script first. The script will create tables and load the tables with data using SQL APIs of Ignite, another approach. And while the database is being loaded, let's check out this script. So my IntelliJ here is not that responsive today, but anyway. So here is I'm creating country tables, so a little bit more columns that we had on this slide. And with the city table, let's check it out. We have this primary key, and we use country code as part of this primary key. But check out here, country code is not defined as an affinity key, which means that even if your country, if your cities share the same country code, they will be distributed randomly. So generally, right now, this rule that all the Canadian cities have to be located on the same cluster node will not take place because we have not set this affinity key. Okay, so let's see what would be the side effect. So the database is preloaded. Let me quickly jump back to the monitoring tool. So these are my tables. We preloaded this data. We created these tables. And I'm going to use SQL notebooks that are available in this management and monitoring tool. I predefined one of the notebooks. The first query is straightforward. Let me run it just to double check that the connection works. So this query returns the most populated countries in the world: China, India, United States are ranked as their top most populated. And the next query is of my interest. So here is I'm going to join data, I'm going to filter data, and basically I want to get the most populated cities among the following countries. I'm interested only in these countries. So right now I'm executing this query. Okay, what's wrong? It went well. And we can see that that's the answer. But I know that that's not the correct answer. Let me show you the correct answer. To do that, I am enabling this flag that will instruct basically Ignite nodes that use data shuffling. It will instruct Ignite server nodes that we will not collocating data, so all the cities are distributed randomly. Use your data shuffling techniques to complete your join properly. And right now, if I run this query, it takes more time. Even too much time. Usually it took like 2 seconds on my laptop to execute this query, but probably that's because my CPUs on my local laptop are in the streaming video. That's why, it took that much time. But remember this answer. That's the right answer, and I can take a screenshot. So basically, Seoul, St. Paul, and Shanghai are the most populated cities among these countries. And it usually takes between 2 seconds and 5 seconds to complete this query. Because why so long time? That's the right answer, but Ignite uses not the most optimized execution plan, and also data is being shuffled between those two cluster nodes. Network is in place. And now let's see how the performance changes if I collocate all the data in advance. So Seoul, São Paulo, and Shanghai are the right answers. And right now I'm going to reload this database with one minor change. While the database is being reloaded, let's jump back to our source code, and here is that script. So it's all the same model, the same records. The only difference is that I'm setting this affinity key. And what will happen is that whenever I will be inserting all these records down below, all the cities that have the same country code will be located on the same cluster node. And that will help me to execute my join using this affinity collocation, and will help me to avoid data shuffling. So just in case, let's refresh the screen. The database was reloaded. Let me check that it works. Okay. And now I no longer need this flag. I know that the data is collocated. You see, I keep executing this query. That's the right answer, Seoul, São Paulo, and Shanghai. And the data is collocated, no any data shuffling. Ignite uses the best optimization plan it could come up with. And that's actually how affinity collocation can help you to boost your performance. In many scenarios, it might not be possible. For some of the scenarios, it might not be possible to collocate all the data, and you will be required to fall back to the less optimized queries that cause data shuffling. But try hard to collocate all your data in advance. If your all related records are stored on the same machine and you run joins or more advanced calculations, then you can avoid or minimize data movement over the network, and you truly can achieve an order of magnitude performance increase, not even for simple key value operations, but even for advanced SQL queries. All right, that was affinity collocation. And the final concept for today is collocated computations. By this point, as you have seen, we used key value and SQL APIs. And there is one common thing between those data processing techniques. Both key value and SQL take your data that is stored on your server nodes on the side of your database and bring those records to your application layer and do some calculations. While this approach works for most of the scenarios, sometimes we run advanced calculations that can process or iterate through large data sets, or that might need to use a lot of CPU powers to complete such calculation. For instance, take some drug discovery or vaccine discovery tasks, or any routes preparations, if you like UPS or any other delivery company. You also need to come up with some best route in your delivery plans, and that's why you will be traversing through many different data sets and coming up with some different options. And collocated computations let us to take our logic, our business logic that can be relatively complex, and send it for the execution to our cluster nodes and to avoid data movement. So in Apache Ignite and in some other in-memory computing products, you can find so-called compute APIs or computational APIs. In fact, those APIs are implementation of MapReduce paradigm. So we are all familiar with MapReduce. The idea is simple. You take your task, you split this task, you map this task to your nodes that store actual data. You do this calculation of those nodes, and then you can execute the reduce phase when those nodes can send you back some result sets, and you just return those final tiny result sets to your application layer. And Ignite supports this API, and you can see that I know that in Ignite this is used for fraud detection when you do payments with your credit cards. It's used for drugs analysis. It's used by companies to calculate delivery routes. It's used for many other needs. So the goal is you have your Java task, you have your .NET or C++ task. You grab this task and send it for the calculation to your server nodes. And here is to give you one of the real business use cases. Quite long time ago, I was involved in one project when a big bank was moving to Apache Ignite, and they had a relatively standard operation. They store millions and millions of different savings accounts, and once a month they had to execute some operation, and in that operation they had to traverse through all those millions of accounts, do some calculations, apply some interest rate, and write back all the changes to the database. They used some well-known relational database, and their application that did that calculation was studied once a month, late night, when the load on the system was minimal. That application would connect to the database, pull all the millions records to the application layer or the network, will do all the processing on the application side and apply the interest rate and write everything back. And usually they had a really powerful hardware, and it took them more than 2 hours to complete this operation. So once they switched to Apache Ignite, once they preloaded a distributed cluster, loaded all the data in memory, applied all the Affinity collocation techniques, they decided just to update their SQL queries and use Ignite SQL capabilities. And they have seen that, all right, yes, right now with that approach, with Ignite SQL, it executes faster. For instance, instead of 2 hours, the same operation was completing in 1 hour, as far as I remember. That was good, but not a breakthrough. And finally, we decided to change this approach. We said that, guys, why do we use SQL to pull data from Ignite cluster and do the calculations on the application? And why don't we take this calculation and send it for the execution to Ignite cluster nodes instead that have all the data locally? And once they did that, they broadcasted this calculation. That calculation traversed all the records that were located locally on every cluster node. And that helped them to significantly reduce their overall calculation time from hours to like 15 minutes. Now with that approach, with collocated computations, that procedure was completed in 15 minutes versus 1 hour with Ignite SQL and versus 2 hours with relational database SQL. So, and here is the story tells us that within memory computing technologies and software, your success depends not only on the fact that you have powerful big cluster with a lot of memory capacity, but also that your applications can minimize or avoid network optimization, because the cluster is a set of interconnected machines. And if you come up with some calculation approach that will help you to avoid data movement, then you can truly get a kind of an order of magnitude improvements, performance increase. And the same logic applies for, let's say, machine learning. Some of the distributed in-memory computing technologies support machine learning APIs. Apache Ignite is not an exception here. And in Apache Ignite, when it comes to the training phase, we also use this collocated approach. When you start the training of your model, then this model training phase is split, and each training phase is executed on every node. And on every node, we are going to use only the local data or only the local training set available on that machine. There might be for sure some of the data shuffling between those nodes during the training phase, but it will be minimized. Okay, and that's how we came to the final example of our today conversation. So I'm just going to show you how it's easy to start a compute task. So what I have here so far, again, I'm going to, let me start this example first, and then I will navigate you through the source code. So what do we have in here? Again, I'm connecting using the same configuration, and then I'm executing this task. So here is we're using Ignite Compute API. I'm broadcasting this task to all my 2 server nodes. I just want them to kind of welcome me, say hello node. And the other compute task also will broadcast this Ignite callable, which is an anonymous class. And then on that node, we are going just to print out all the details about the system, like operating system, Java runtime, etc. So I do believe that this calculation has already completed. So let's go to my terminal window and check the output of my cluster nodes. You can see that this logic was executed on my cluster nodes, my cluster machines. That's how it works. It's simple. And here as we are using Java, you can use, for instance, right now we support the same APIs for .NET and C++. Finally, one more thing that I'd like to show you. With this collocated computations approach, you truly can decouple your application logic from your cluster maintenance. So for instance, let's decide that you want to update your class. You change your logic, you decided to improve it. And does it mean that you need to restart your Ignite cluster and reload the data? You don't. What happens next? Let me create some private class. I will add some fields. Page and string name. Next, I need a constructor for these fields, and also I want my development environment to implement toString method for me. Okay, the class is ready. And next, what I'm doing, I want to update my compute task. I'm creating this class. Some random name and age. And here is, I just do this. I want to print out the name of this person. Ready. So what happens next? I'm going to restart this application. The application will recompile this class. That will be a brand new class. And then I will send this class, updated class, for the calculation to my two server nodes. And what's important here, I am not restarting these server nodes. I'm not updating the jar files. So what Ignite will take, Ignite server nodes will see that this class has changed, and they will reload everything, the bytecode. They will reload the bytecode over the wire from my application to these cluster nodes. You see? So the calculation completed, and my cluster nodes just basically say, all right, I need to reload this calculation. I'm reloading the class, the bytecode, and that's it. And you as application developer, you're decoupled from the cluster maintenance. The cluster is running. You are free to update your computation. You can change your Java, .NET, or C++ classes, and everything will be reloaded for you in background by Ignite. So that's how you can work. All right, guys. I would say that we made it. As a summary, right, before we move to the closing part of this presentation, what we have learned so far. The goal of this session was to introduce you to some fundamental or essential concepts of in-memory systems that are quite generic. So we used Ignite as a reference today, but I do believe that you will find out that the same concepts, some of these concepts and techniques are applied by other in-memory caches, data grids, and databases. Partitioning. Partitioning helps us to use all the memory capacity and CPU cores of our distributed system. It distributes data across a cluster of machine for us. Affinity collocation, the second concept. That's a technique that can truly help us to avoid data shuffling, to minimize network utilization. Especially that's useful and handy for SQL with advanced queries like joins, group bys, etc. And collocated computation. That's an API that can let you to run advanced or compute or data-intensive calculations, avoiding any data movement over the network. And just remember those tables with latencies. Memory is much faster than disk, but disk is much faster than network. And that's why when you're dealing with memory computing systems, you have to care of both. Yes, allocate, provision a powerful enough in-memory cluster, but also do your homework when you're designing your system. Ensure that your applications using affinity collocation for data distribution, and also whenever is needed, you are using collocated computations to run your advanced calculations on the cluster nodes. And Apache Ignite, as an Apache Ignite member and representative, I will be pleased if you try out Apache Ignite and see if it works for your scenarios. So come to us, ask questions, try out. And also, if you are interested in Ignite as a contributor, if you'd like to become an Ignite developer who contributes to Ignite, welcome. So if you want to learn how to build distributed systems, how to design distributed compute APIs, SQL, machine learning, and transactions, there are many interesting areas where you can learn or gain more skills. So come to us and help to make Ignite much better and more powerful. And here is just some resources. So once you download the slides, here is documentation, the projects that I used throughout this session, and also mailing lists. Feel free to ask the questions there. Thanks, you made it. That's it, and I'll be happy to answer any questions that you might have.
Okay, thank you, Dennis. We have quite a few questions here. We'll see how many we have time to cover. First of all, what is the distance between nodes when latency starts affecting the computational performance of the GridGain platform?
Let me see if I understand this question properly. So I think that primarily, and that's not only about GridGain, that's about in-memory distributed in-memory systems in general. I would say that it depends on your APIs usage, right? You've seen that how this affinity collocation helped us to boost performance of my relatively simple SQL query. When instead of like seconds, it started the query started executing in milliseconds. But also, let's say that you're just creating some solution to cache your web sessions or sessions of your phone calls, etc. You might not need any SQL APIs. You might want to use only key value APIs. Do you need to use any affinity collocation consents? Probably not, at least not at this stage, because all you need to do is just to provision a cluster, load data there, and deploy as many nodes as you need to meet your SLAs and latency requirements. If you see that network becomes your bottleneck, like with SQL queries that can cause data shuffling, try to optimize SQL and also double check that you have applied all the affinity collocation techniques. And for the collocated compute, I mean that I see it used a lot for by pharmaceutical companies, by logistic companies, by financial companies, because in many of these cases, companies need to traverse through large data sets, and they just basically take and move their application logic for the execution cluster message. Just decide on your requirements. All this, everything that you have been introduced today, it's not just a strict rule to follow, but just some basic principles and concepts you need to keep in mind depending on the stage of your application evolution and depending on your current needs. Hope I answered your question. If it's not what you asked for, please ask a follow-up question to me.
Okay. Next question. In the in-memory model, does the memory have to be the same size as the third-party data store?
Good question. Actually, excellent question. So in the in-memory mode, that's the case when Ignite does not, let's say, persist changes in its own native persistence, and you can use a relational database as a disk storage. So in this case, it depends again. So for instance, let's say that you use key value APIs only. And with key value APIs, we support read-through capability, which means that if you run this key value request and Ignite finds out that this record is not located in Ignite cluster in memory, then Ignite will connect to your relational database and read that value from the database, and it will appear in your Ignite cluster. And at the same time, Ignite can kind of evict some of the entries if you set up eviction and expiration policies. But this read-through capability does not work for SQL. So if you use SQL queries or scan queries or probably there are some other advanced APIs in Ignite, then you have to load all the data in memory, because Ignite will not be able automatically to go to your relational database and query, let's say, a range of records, because for SQL, usually you are requesting a range of records, and Ignite will not be able to find out what exactly to request for the database. That's why, let's say, if you use Ignite is in a pure in-memory mode, if you use only key value APIs, then yes, you do not need to keep all the data in memory. Ignite will read through records from your relational database as an option. If you use SQL, you have to load all the data in memory. If you cannot load all the data in memory and you have to use SQL, then use Ignite native persistence. You can start Ignite cluster, you can enable persistence, you will keep all the data on disk and subset in memory. If you run SQL or another advanced, or you use another advanced API, then Ignite will read all the missing records from disk if anything isn't available in memory. That's it.
Okay. Since memory is managed in Apache Ignite off heap in order to avoid Java garbage collection issues, how would high-level system memory configuration, for example, between persistent memory and working scratch memory, be accomplished?
So here is that's a good point. With this session, we are not diving into the details of Ignite implementation, because primarily the goal of this session is to introduce you to these generic concepts, which are kind of implemented relatively similar in other products. In Ignite, if to talk about Ignite memory system, that's true to say that Ignite stores all the data in off-heap regions that are not garbage collected, but still, as a Java middleware, Ignite is still Java middleware application. We utilize Java heap. And with Java heap, we will be putting some of the result sets, temporary objects in heap, etc. And here is again, guys, there is no any generic rule of thumb. Usually, depending on your workload, depending on your SLAs, you give Ignite. First of all, you just decide, you know how much data will be storing. So that's will guide you through the memory capacity you need to allocate for the off-heap regions, because you need to keep all this data indexes in off-heap. But then once you start running your first operations, you will see how much memory you need for Java heap, because all your queries, operations will be reading data from off heap to Java heap for a short period in time, and you need to keep up, you know, with garbage collection rates. So generically for some average projects, I would say that I see that usually it's like around 2 or 4 gigabytes Java heaps we have, but it can be larger. And also, depending on use case, if you're dealing with low latency scenarios, when you each operation has to complete, let's say, in 10 milliseconds or microseconds for high percentiles, like 99.49 percentiles, then here is some of our users switch to pause-less garbage collectors. For instance, you know that like there is one company, Azul, they develop their own proprietary C4 garbage collector, and we tested Ignite with that collector, and those Ignite with Azul Zine virtual machine are used for low latency scenarios like 5G like workloads, or let's say fraud detection, credit card payments. All those applications use pretty strict SLAs, like low milliseconds for high percentiles. So again, as a summary, it depends on you, but usually how you do this, you know your data size, you will preload your data, and you will know how much memory space you need to allocate for off-heap memory of Ignite. And then once you start your first benchmarks, running your calculations, you will understand how much Java heap is needed per cluster machine. There are certainly some optimization techniques. You will do optimizations to kind of get all the best from your available resources. And then final resort, if you are dealing with low latency scenarios and you truly need to avoid all the garbage collection options, instead of standard JDKs, you can check garbage collectors and GVMs of the kind Azul develops.
Okay, question, does the SQLine tool come with the Ignite distribution?
Right, yeah, we decided, you know, that was a discussion on our dev list a long time ago, but we decided to package it together with Ignite. Let me show you how it looks like. Let me tweet this. So generally, that's it. It's here. It's Apache Ignite 2.76 release. It's located in build folder. So it's over here. You don't need to download it separately. So we packaged it.
Okay. Question is, if we have two caches with the same affinity key created at 2 different times, then records from these 2 caches with the same affinity key will land on the same node?
Right, that's right. Because if to show you this slide again, yeah, this one. So this part, affinity key to partition mapping, that's just a hash function. We know how hash tables or hash maps are designed. You take your key and you map this key to one of the hash table buckets, right? Using some predefined function, and that is always kind of the same transformation. So we are going to map this affinity key to partition. It's all the same. If affinity key is the same, that all the records will be located in the same partition. And when you're talking about two different tables, by default, every table, it's understood that, let's say, partition number 10 will be located in one table, and also there will be partition number 10 in the other table. And by default, all the partitions of different tables that have the same number, they will be located on the same cluster node. So it doesn't matter, like you can have 10 different tables, and partition 10 of those 10 different tables by default will be stored in Ignite on the same cluster machine. And that's why when, let's say, you're mapping like city, records of one table that have one affinity key, the records of another table that have the same affinity key, they will be mapped to the partition, let's say 10 of their tables, but all those partitions are located on the same cluster machine. So that's how partitioning works in Ignite by default. Hope it's clear. If it's not clear, feel free to send me a question to the dev list or user list. I hang out there and we can discuss it in details.
Okay, very good. We're out of time. So just a reminder, we have recorded today's session, and we will send an email with a link to the recording as well as a link to today's slides out within the next 24 hours. Please look for that in your inbox. We have a number of new webinars that were added to our website yesterday, and a number more that we're going to be adding over the next couple of days. So if you have more questions, please take a look. There may be a upcoming topic that's of interest to you. Thanks, Dennis. Thanks, everyone, and have a good day.
Thanks, everyone, for joining. Enjoy your day.